Electricity and magnetism are interrelated and are also interconvertible. Let us look at a few examples. In this setup, an electric current passing through a conductor produces a magnetic field, which can be observed through the deflection of a magnetic compass needle placed near the conductor. This proves that moving electric charges produce magnetic fields. Electric motors work on this principle. However, in this setup, we see that an electric current is induced in a closed coil when subjected to a changing magnetic field. The phenomenon in which an electric current is generated by varying magnetic fields is called electromagnetic induction. Electric generators work on this principle. We will now discuss and learn about 3 experiments by Faraday and Henry relating to electromagnetism. In the first experimental setup, a coil is connected to a galvanometer. When a bar magnet with its north pole facing the coil is moved towards or away from the coil, the galvanometer needle deflects to the right and left side of 0 reading respectively, showing the presence of a current in the coil. Now, let us see what happens if the south pole of the magnet faces the coil. The galvanometer needle deflects to the left side of 0 reading as the magnet approaches the coil and deflects to the right when the magnet moves away from the coil, showing the presence of a current in the coil. The galvanometer needle deflects only as long as the bar magnet is in motion. Once the bar magnet comes to rest, the galvanometer needle settles down at 0 reading, indicating that there is no current in the coil. From all these observations, we can conclude that whenever there is relative motion between a bar magnet and a coil, an electric current is induced in the coil. In the second experimental setup, there are 2 coils. Coil 1 connected to a galvanometer, coil 2 connected to a battery. Due to the steady current in coil 2, a steady magnetic field is set up around the coil 2, and this magnetic field is also linked to the coil 1. When coil 2 is kept stationary and coil 1 is moved towards coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the left of 0. When coil 2 is kept stationary and coil 1 is moved away from coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the right of 0. If we keep coil 1 stationary and move coil 2 towards coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the left of 0. Now, if we keep coil 1 stationary and move coil 2 away from coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the right of 0. From all these observations, we can conclude that whenever there is relative motion between a current-carrying coil and a closed coil in which a galvanometer is connected, a current is induced in the closed coil. In the third experiment, a tap key is provided in the coil 2 circuit. Here, we can observe the deflection of the galvanometer needle even when the 2 coils are stationary. This deflection is observed only at those instants when the tap key is either switched on or off. This happens because of the change in magnetic field during switching on and off. When a ferromagnetic material like an iron rod is placed coaxially along the two coils, the effect of the magnetic field linked to the coil 2 increases due to the nature of the ferromagnetic material, as it allows more number of magnetic lines of force to link within the area of the coil. Hence, the deflection of the galvanometer needle increases, indicating an increase in the induced current. Before attempting to understand Faraday's law of electromagnetic induction, we should recapitulate the terms used in electromagnetic induction. These terms are representation of a surface area by a vector A, uniform magnetic field B, and magnetic flux phi B. The area of a plane surface is represented by a vector A drawn along the outward normal to the plane surface. In the case of a curved surface, the surface area is split into very small areas, and each is approximated to a planar area. In a uniform magnetic field B, the number of magnetic field lines cutting across an area placed perpendicular to the field lines is same for each unit area of the surface. If a plane of area A is placed in a uniform magnetic field B with its area vector A, making an angle theta with the magnetic field, then the magnetic flux phi B through the area can be written as phi B is equal to B dot A, which is equal to BA cos theta. Let this be equation 1. Magnetic flux phi B can be varied by changing any one or more of the terms B, A, and theta. The SI unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux phi B is a scalar quantity. When the magnetic field has different magnitudes and directions at the various parts of a curved surface, the magnetic flux through the curved surface is computed by extending equation 1. Phi B is equal to B1 dot dA1 plus B2 dot dA2 plus and so on, which is equal to sigma all Bi dot dAi. Let this be equation 2. So far, we have recapitulated the terms used in electromagnetic induction. Let us now learn about Faraday's experiments where we use these terms. Faraday conducted 3 experiments, from which he concluded that an EMF is induced in a coil when the magnetic flux cutting across the coil changes with time. In the first experiment, Faraday observed that the relative motion between a magnet and a coil changes the magnetic flux across the coil. This change in magnetic flux with time induces an EMF in the coil. Similarly, in the second experiment, he observed that the relative motion between the two coils, one carrying a current, changes the magnetic flux across the coils. This change in the magnetic flux with time induces an EMF in the other coil. In his third experiment with 2 coils, he found that if the tap key is pressed, the current in coil 2 and the resulting magnetic field rises from 0 to maximum value in a short time. This results in a change in the magnetic flux with time across coil 1, inducing an EMF in it. If the key is kept pressed, there is a steady magnetic field across coil 1. Thereby, there is no EMF induced in it and the current drops to 0. When the tap key is released, the current in coil 2 decreases from a maximum value to 0 in a short time, resulting in the magnetic flux across coil 1 to drop suddenly, thereby inducing an EMF in it. From the observations of these 3 experiments, Faraday concluded that the time rate of change of magnetic flux through a closed coil induces an EMF through it, and stated the Faraday's law of electromagnetic induction. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. We can put this law in the form of a mathematical equation. E is equal to minus d phi b divided by dt. Let this be equation 3. In this equation, E is the induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. When n number of turns are closely wound to form the coil, the change of flux with time for each coil is the same, and we can write for the total induced EMF as E is equal to minus n into d phi b divided by dt. Let this be equation 4. In this equation, E is the total induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. Therefore, the total induced EMF can be increased by increasing the number of turns n of the coil. Before attempting to learn about Lenz's law, let us first recapitulate about the right-hand grip rule applied to a current-carrying coil. Consider a right-hand fist with the thumb extending out. If the fingers are wrapped in a circle pointing in the direction of the current through the coil, then the thumb points towards the end of the coil, indicating the north pole. Lenz's law helps us in identifying the polarity of the induced EMF in a coil. Lenz's law states that the polarity of induced EMF in a closed loop is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. We can put this statement in simple terms. If a current is induced by an increasing flux, it will weaken the original flux. If a current is induced by a decreasing flux, it will strengthen the original flux. The magnitude of the induced EMF is given by Faraday's law, which is E is equal to minus d phi b divided by dt, where E is the induced EMF in the coil and phi b is the magnetic flux. The negative sign in this equation represents the effect as stated in Lenz's law. Let us look at Faraday's experiments and apply Lenz's law to them. To identify the polarity of the induced EMF and the direction of induced current in the coil. In this experiment, the coil, which is connected to a galvanometer, is at rest. A bar magnet with its north pole facing the coil is moved towards the coil. This causes the magnetic flux through the coil to increase. A current is induced in the coil which opposes this increase in flux. The induced current is in a counterclockwise direction, looking from the bar magnet side. This current produces a north polarity towards the north pole of the magnet and opposes the motion of the magnet, thereby opposing the increase in magnetic flux through the coil. A force is required to move the magnet against this repelling force. The same magnet, when moved away from the stationary coil, causes the magnetic flux through the coil to decrease. A current is induced in the coil which opposes this decrease in flux. The induced current is in a clockwise direction looking from the bar magnet side. This current produces a south polarity towards the north pole of the receding magnet. This south pole attracts the north pole of the bar magnet, thereby resisting the motion of the magnet. When the south pole of the magnet is towards the coil and it is moved towards the coil, a south polarity is induced near the south pole of the magnet. When the same magnet is moved away from the coil, a north polarity is induced near the south pole. In all these experiments, we can also use an open circuit in the place of a closed loop. In this case too, an EMF is induced, but there is no induced current in the coil. The direction of this induced EMF can be found using Lenz's law. Here is an easy way to understand the direction of induced currents and EMF. We have so far taken Lenz's law for granted. Suppose that the induced current is in the direction opposite to the one given in the figure. In that case, the south pole due to the induced current will be near the approaching north pole of the magnet, causing the bar magnet to be attracted towards the coil. A gentle push on the magnet will start the process of motion, and its velocity and kinetic energy will continuously increase without expending any energy. If this is true, we can construct a perpetual motion machine with a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. So, we can conclude that Lenz's law is correct. In all the experiments discussed, a force is required to move the magnet bar either towards or away from the coil. The product of the force and the distance moved gives the work done on the magnet. The work is done by spending some mechanical energy by the person conducting the experiment. The mechanical energy is converted to electrical energy in the coil. The electrical energy is converted into heat energy by heating up the coil, which is dissipated into the atmosphere. From these observations, we can say that the energy is only converted from one form to another, or the energy is conserved. We have studied about induced EMF in a circuit due to the rate of change of magnetic flux through the circuit. This happens due to the relative motion between the coil C1 and the bar magnet. We know that the induced EMF E is equal to minus d phi by dt, where d phi by dt is the time rate of change of the magnetic flux and the minus sign is in accordance with the Lenz's law. Let this be equation 1. Now let us study about induced EMF produced due to the motion of a conductor in a magnetic field. Consider PQRS to be a rectangular metallic loop having a galvanometer G connected between R and S. The part PQ can slide forwards or backwards in between the parts PS and RQ of the loop. Let us now place PQRS in a uniform magnetic field such that its plane is perpendicular to the magnetic field. For a time-independent magnetic field, the magnetic induction B remains constant both in magnitude as well as direction. Let the length of PQ be L and that of RQ be X. Let the conductor PQ move towards the ends SR with a constant velocity V. We observe that the conductor PQ, the direction of the magnetic induction B, and the velocity V of the conductor are mutually perpendicular to each other. we see that the conductor initially is at a distance x from the RS end. As the conductor moves towards the RS end, it is displaced from its original position and its velocity v can be written as dx by dt. Since the plane of the loop is normal, that is, perpendicular to the magnetic field, maximum magnetic flux passes through the loop. This magnetic flux, phi b, passing through the loop is equal to the product of the magnetic induction B and the area A of the enclosed loop. The product of L and X represents the area swept A. Hence, we can now rewrite the magnetic flux phi B as equal to BLX since A equal to LX. As the conductor moves towards the RS end, we see that X is varying and hence the area A enclosed by the loop also changes with the time. Therefore, we see that magnetic flux phi B also changes with time as the magnetic flux depends on the area enclosed. Hence, according to principle of electromagnetic induction, an induced EMF is developed across PQ. This induced EMF, E, is equal to minus d phi b by dt as given by equation 1. Substituting for phi b, we get E is equal to minus d by dt of BLX. As B and L are constant and only X is the variable, we can write E is equal to minus BL into dx by dt. As dx by dt represents the velocity v of the conductor PQ, we can write electromotive force E is equal to minus BLV. Let this be equation 2. The induced EMF E is also called the motional EMF in this case. The concept of motional EMF can also be explained by using the Lorenz's force acting on the free charge carriers of conductor PQ. We know that when a charge Q enters perpendicular to a uniform magnetic field of induction B, then the Lorenz's force on the charge FB is equal to QVB. As the conductor moves with a speed v, free electrons in the conductor also moves with speed v in the magnetic field B in addition to the random velocity they have within the metallic conductor PQ. The average magnetic force due to the random velocity is 0. But the average magnetic force on each free electron due to velocity v is Fb equal to QVB, where Q is the charge on the electron equal to minus 1.6 into 10 power minus 19 coulomb. From Fleming's left-hand rule, we can say that in this situation, the magnetic force on a positive charge moving with velocity v in this magnetic field will be along PQ. In accordance with the same rule, we can see that the force on the electrons Fb will be directed along QP. And we see that the free electrons in the conductor move towards P. As a result of this movement, a negative charge builds up at P and a positive charge appears at Q. An electric field is developed within PQ such that the electric field exerts a force Fe equal to QE on each electron. In electrostatic equilibrium, the force Fe will be equal to Fb, and this build of charge stops. Since Fe becomes equal to Fb, we have QE equal to QVB. Simplifying, we get E equal to Vb. Due to the charge buildup, a potential difference is developed across PQ, which is the induced EMF E. We know that the potential difference E is equal to E into L. Substituting the value for the electric field strength E equal to VB, we get induced EMF E equal to BLV. Since Lenz's law is obeyed here also, we can write this induced EMF as E equal to minus BLV. This induced EMF E is the motional EMF. Due to the induced EMF, an induced current flows in the closed loop PQRS, and the current can be detected by the galvanometer. This induced current flows along the path QRSP. This equation for the motional EMF derived in this manner is the same as the equation 2 which we derived earlier. Now, consider the case when the conductor PQ is stationary in the magnetic field, but the magnetic field varies with time. That is, its magnitude or direction, or both magnitude and direction are changing with time. Since the conductor is at rest, its velocity v is equal to 0, and as seen earlier, the magnetic force Fb equal to QVB is 0. The moment the magnetic field starts varying, an induced current flows in the loop which can be detected by the galvanometer. Since the magnetic field force Fb is 0, the electrons are forced to move only by the electric field, and hence we conclude that an electric field appears instantaneously. This electric field is produced by the changing magnetic field and is called the induced electric field. This electric field causes an EMF to be developed in the loop, and hence an induced current flows in the loop. From these observations, we can say that just like the moving charges in a conductor can produce magnetic fields and exert a magnetic force on a magnet in its field, a varying magnetic field can also exert a force on stationary charges. So, if we move a bar magnet towards a stationary charge, the charge experiences a force due to the varying magnetic field. This is the fundamental significance of Faraday's discovery. Consider a rectangular conducting loop PQRS placed in a uniform magnetic field of strength B. The arm PQ of the loop can be slit over its arms PS and QR. Arms PS and QR of the loop are part of the rails SM and RN connected to SR. The length of SR is L. The length of the arm PS at an instant is X. Let the electrical resistance of PQ be R. Let us assume that the resistances of the rails SM, RN and the link SR is negligible compared to the resistance of arm PQ. Hence, the overall resistance of the rectangular loop is R. The flux through the loop at any instant, phi B, is equal to the product of the strength of the magnetic field B and the area enclosed A. Here, area of the loop A is equal to the product of the breadth and length of the loop L and X. In this case, the instantaneous flux phi B is equal to BLX. Let this be equation 1. From Faraday's law, we get induced EMF E is equal to minus d phi B by dt. The negative symbol is in accordance with Lenz's law. On substituting phi B from equation 1 and simplifying, we arrive at the equation E is equal to minus dBLX by dt. The strength of the magnetic field B and the length of the arm SR of the loop L are constant. Hence, the equation transforms to E is equal to minus BL dx by dt. But dx by dt is the instantaneous velocity v of the arm PQ of the loop, which is directed towards the SR part of the loop as shown. Hence, E is equal to minus BLV. Let this be equation 2. This EMF is the motional EMF as discussed earlier. As the resistance of the rectangular loop is R, the magnitude of the induced current, I, is equal to the magnitude of E by R. The current is directed from P to Q in the arm. Substituting the value of E from equation 2, we arrive at the equation I is equal to BLV by R. Let this be equation 3. As the current carrying arm, PQ, is in the magnetic field, there exists a force on the arm. The direction of this force acting on the arm PQ is given by Fleming's left-hand rule. According to the rule, the thumb, the forefinger, and the middle finger of the left hand are stretched such that they are mutually perpendicular. If the forefinger and the middle finger indicate the directions of the magnetic field and direction of the current respectively, the thumb indicates the direction of the force. Thus, as per the rule, the direction of the force on PQ is opposite to the direction of the motion of the arm PQ. Vectorially, the force on the arm PQ is given by F is equal to I L cross B, and this force arises due to the drift velocity of charges, responsible for the current along the arm and the consequent Lorenz's force acting on them. Hence, the magnitude of the force F is equal to ILB sine theta, where theta is the angle between the directions of the current and the magnetic field. Here, the angle between the arm PQ and the magnetic field is 90 degrees. Hence, the equation for the magnitude of the force transforms to F is equal to ILB sine 90. As sine 90 is equal to 1, this can be rewritten as F is equal to ILB. Let this be equation 4. On substituting equation 3 in equation 4 and simplifying, we get F is equal to B square L square V by R. Let this be equation 5. This force arises due to the drift velocity of the charges through the arm PQ that are responsible for the current and the Lorenz's force on them. If we need to maintain uniform velocity for the arm PQ, we need to apply a constant force F in the direction of the velocity. The applied force must be equal in magnitude and opposite in direction to the magnetic force. Thus, the power required to push the arm PQ along the rails is given by the equation P is equal to FV. On substituting the value of F from equation 5 and simplifying, we get the equation P is equal to B square L square V square by R. Let this be equation 6. Notice that the work done in moving the arm PQ is mechanical in nature. This mechanical energy is converted into heat energy when the work is done. This energy, referred to as joule heat, is given by Pj is equal to I square R. On substituting the value of I from equation 3 and simplifying, we get Pj is equal to B square L square V square by R. Let this be equation 7. Notice that the right-hand sides of the equations 6 and 7 are equal, thereby confirming the law of conservation of energy. Thus, mechanical energy which was needed to move the arm PQ is converted into the induced EMF and then to thermal energy. Thus, we conclude that the induced EMF in a conductor when moved in a magnetic field is in accordance with law of conservation of energy. Let us now study the relationship between the flow of charge through the arm PQ and the flux. From Faraday's law, we have learned that the magnitude of the induced EMF modulus E is equal to change in magnetic flux delta phi B by delta T. Let this be equation 8. However, the EMF induced in the circuit is equal to IR. But rate of charge flow is current. Hence, current can be replaced by delta Q by delta T. Let this be equation 9. The left-hand sides of equations 8 and 9 are equal. Equate the right-hand sides to arrive at the equation delta Q is equal to delta phi B by R. We use an apparatus that allows a copper plate to swing back and forth through a magnetic field like a pendulum. The plane in which the copper plate swings is parallel to the plane of the plate and normal to the direction of the magnetic field. As the copper plate enters the field, the changing magnetic flux induces an EMF in the plate, which in turn causes the free electrons in the plate to move, producing circulating eddy currents. Note that the magnetic field is directed from the north pole to the south pole of the magnet that provides the field. When viewed from the north pole side of the magnet, the induced eddy current is counterclockwise as the plate enters the field. As the plate enters the magnetic field, the external magnetic flux through the plate increases. Hence, by Lenz's law, the induced current must provide effective magnetic poles on the plate that are repelled by the poles of the magnet. Thus, here a north pole is induced over the surface of the plate facing the north pole of the magnet. As the plate leaves the magnetic field, the external magnetic flux through the plate decreases. Hence, again as per Lenz's law, the induced current must provide a magnetic south pole on the surface of the plate facing the north pole of the magnet. This is quite opposite to the case when the plate enters the magnetic field. The induced eddy current always produces a retarding force Fb when the plate enters or leaves the field. This retarding force slows down the swinging of the plate and eventually brings it to rest. Thus, the oscillations of the plate are damped. When rectangular slots are cut in the plate, eddy currents and the corresponding retarding force are greatly reduced. This reduction in the retarding force is because the rectangular cuts in the plate prevent the formation of large current loops. Hence, the pendulum plate with holes or slots reduces electromagnetic damping and the plate swings more freely. Let us now explore the uses of eddy currents. Eddy currents are produced when a metal plate is subjected to a changing magnetic field, heats it. Hence, these currents are unwanted in certain situations. Reduction in the surface area of the plate helps in reducing eddy currents in the metallic cores of transformers, electric motors, and other such devices, in which a coil is wound over a metallic core. Eddy currents are minimized by using laminations of metal to make a metal core instead of using a single metal piece. The laminations are separated by an insulating material like lacquer. The plane of the laminations is arranged parallel to the magnetic field, such that it cuts across the eddy current paths. This arrangement reduces the strength of the eddy currents. Since the dissipation of electric energy into heat depends on the square of the strength of the electric current, heat loss is substantially reduced. Let us now study the applications of eddy currents. Strong electromagnets are situated above the rails in some electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. As there are no mechanical linkages, the braking effect of the train is smooth. Certain galvanometers have a fixed core made of a non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the core oppose the motion and bring the coil to rest quickly. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. A high-frequency alternating current is passed through a coil which surrounds the metals to be melted. The eddy currents generated in the metals produce high temperatures sufficient to melt it. The shiny metal disc in the analog type electric power meter rotates due to eddy currents. Electric currents are induced in the disc by magnetic fields produced by the sinusoidal varying currents in the coil. Consider a circuit consisting of a coil having n number of turns connected to a source of EMF in which current can be varied with time. When the source current is in the direction shown, a magnetic field directed as shown is set up inside the coil. When the source current changes with time, the magnetic flux through the coil also changes and induces an EMF in the coil. This phenomenon is called self-induction. The flux linkage through a coil of n turns is proportional to the current through the coil and is expressed as n phi b is directly proportional to I. Replacing the proportionality symbol with a constant, we get n phi b is equal to L times the current I, where the proportionality constant L is called the self-inductance of the coil. Let this be equation 1. L is also called the coefficient of self-induction of the coil. When the current in the circuit is varied, the flux linked with the coil changes and an EMF is induced in the coil. This means d by dt of n phi b equals to L di by dt. Let this be equation 2. From Faraday's law, for a coil of n turns, the self-induced EMF E is equal to minus d by dt of n phi b. Let this be equation 3. Comparing equations 2 and 3, we get the equation E is equal to minus L di by dt. Let this be equation 4. It is important to know that from Lenz's law, the polarity of this induced EMF is such that it opposes the change in the magnetic field from the source current. Even Faraday's equation confirms that the self-induced EMF opposes any change of current in the coil. Thus, this self-induced EMF is also called back EMF. The self-induced EMF plays the role of inertia. It is the electromagnetic analog to mass in mechanics. Hence, work needs to be performed to establish a current in a circuit, and it is stored as magnetic potential energy. For a current I, at an instant in a circuit, the rate of work done is dW by dt is equal to modulus of E times I. Let this be equation 5. On substituting the magnitude of E from equation 4 in equation 5 and simplifying, we get dW by dt is equal to Li di by dt. Let this be equation 6. The total amount of work done can be established by integrating equation 6 on both sides. Thus, we get integral dw is equal to integral over 0 to I, Lidi. Thus, the work done or energy consumed in establishing a current in the circuit is W is equal to half Li square. This expression is similar to the expression for kinetic energy of a particle of mass m moving with velocity v, which is given by E is equal to half mv square. This clearly shows that self-inductance L in electromagnetic induction is analogous to mass m in mechanics. Thus, self-inductance is the measure of electrical inertia. It opposes the growth and decay of the current in a circuit. Let us now calculate the self-inductance of a long solenoid. Let the length of the solenoid be L, the current through it be I, the number of turns be N, and its area of cross-section be A. Let the number of turns per unit length of the solenoid be N, which is equal to N by L. The magnetic field induced in the solenoid due to the current I is B is equal to mu naught Ni. Let this be equation 7. Here, we neglect the edge effects of the solenoid, thus assuming the magnetic field in the solenoid to be uniform throughout. The magnetic flux is equal to the product of the magnetic field strength and the area. Thus, phi B is equal to BA. Let this be equation 8. Using equation 7 and equation 8, we get the total flux linked with the solenoids is N phi B is equal to NL into mu naught Ni into A. Simplifying the expression, we get N phi B is equal to mu naught N square ALI. Let this be equation 9. We have already established that N phi B is equal to L times the current I. Comparing this expression with equation 9 and simplifying, we get the value of L as L is equal to mu naught N square AL. Let this be equation 10. If the space in the coils of the solenoid is filled with the material of magnetic permeability mu r, then L is equal to mu r mu naught N square AL. Let this be equation 11. Note that the self-inductance of the solenoid depends on the geometry and the permeability of the medium. An AC generator converts mechanical energy into electrical energy. In its simplest form, an AC generator consists of a rectangular coil mounted on a rotor shaft. The coil is also referred to as the armature. The coil is placed in a uniform magnetic field. The axis of the coil is normal to the direction of the magnetic field. The coil, or the armature, is mechanically rotated in the uniform magnetic field by some external means. Let the number of turns in the coil be N. The ends of the coil are connected to an external circuit by means of slip rings and brushes. The coil rotates, inducing an EMF and a current in itself. The current induced in the coil is fed into external circuits through the slip rings that act as terminals to the generator. Let us now find the expression for the EMF generated by an AC generator. Consider the area vector A for the coil. The area vector is normal to the plane of the coil. Initially, let the area vector lie in the direction of the magnetic field. This implies that plane of the coil is normal to the direction of the magnetic field. Let theta be the angle between the area vector A and the magnetic field B at a given instant of time t. When the coil is rotated at a constant angular velocity omega, the value of theta at the instant of time t is given by the equation theta is equal to omega multiplied by time t. Let this be equation 1. The effective area of the coil which is linked with the magnetic field is A cos theta. From equation 1, it is clear that the effective area of the coil is a time-dependent function. In other words, the rotation of the coil causes the magnetic flux through it to change, thereby inducing an EMF in the coil. The flux induced in the coil at any instant of time is given by the equation phi b is equal to BA cos theta. Let this be equation 2. On substituting equation 1 in equation 2 and simplifying, we get the equation phi b is equal to BA cos omega t. Let this be equation 3. From Faraday's law, the induced EMF for a coil of n turns rotating in a magnetic field is given by E is equal to minus nd phi b by dt. The negative sign is in accordance with Lenz's law. On substituting the value of phi b from equation 3 and simplifying, we get E is equal to minus nd by dt of BA cos omega t. The strength of the magnetic field B and the area of the coil A are constants. The equation now transforms to E is equal to minus nBAd by dt of cos omega t. From differential calculus, we have d by dt of cos omega t is equal to minus omega sin omega t. Hence, the instantaneous value of the EMF E is equal to nBA omega sin omega t. Let this be equation 4. Note that nBA omega is the maximum value of the EMF that occurs when the value of sin omega t is plus or minus 1. That is, when theta is 90 degrees, or 270 degrees. This is because the change of flux is the maximum at these two angles of the coil. As the value of sine function varies from plus 1 to minus 1, the sign or polarity of the EMF changes with time. Accordingly, the direction of the induced current changes periodically. For this reason, this current is called an alternating current. Let us denote the maximum EMF nBA omega as E0. Then, the instantaneous EMF E is equal to E0 sin omega t. Let this be equation 5. We know that omega is equal to 2 pi nu, where nu is the frequency of revolution of the generator's coil. Substituting the value of omega in equation 5, we get E is equal to E0 sin 2 pi nu t. Let this be equation 6. Thus, equation 6 gives the expression for the instantaneous value of the EMF. Earlier we have learned how an electric current is induced by the relative motion between a closed coil and a magnet. Electric currents can also be induced in a closed coil by causing a change in the magnetic flux. produced by its relative motion with another current-carrying coil in its vicinity, or by a flux change produced by the same coil. Let us first understand the experimental setup that helps us demonstrate this phenomenon. The coil on the left is called the primary coil and is connected to a battery. Let the current in this coil be I1. The coil on the right is called the secondary coil and it is connected to a galvanometer. The primary and the secondary coils are placed coaxial and an iron core runs along the axes of the coils. Let B be the magnetic field strength due to the current in the primary coil. When the secondary coil is moved towards the primary coil, the magnetic flux through the secondary coil increases. As a consequence of the increasing flux in the secondary coil, the current induced in it increases as it moves towards the primary coil. Let the current induced in this coil be I. When the secondary coil moves away from the primary coil, the magnetic flux through the secondary coil reduces. As a consequence of the decreasing magnetic flux, the current in the secondary coil decreases. The magnetic flux in the secondary coil, phi B, is directly proportional to the current I in it. The variations of the current in the secondary coil are directly proportional to the variations in the magnetic flux. Thus, the rate of change of flux is directly proportional to the rate of change of current. Let the number of turns in the secondary coil be N. Hence, the net flux change in the secondary coil, N phi B, is directly proportional to I. The term N phi B is called flux linkage. The constant of proportionality M between the flux linkage and the current is called the mutual inductance of the coil. Inductance is a scalar quantity and has the dimensions ml square T power minus 2 A power minus 2. The SI unit of inductance is Henry, named after the scientist Joseph Henry, and is denoted by H. 1 Henry is equal to 1 Tesla meter square per ampere. So far, we have explored the experimental setup with two coils of the same radius placed beside one another. Let us now consider an example in which two coaxial solenoids induce current into one another. Consider two coaxial solenoids S1 and S2 of length L. Let the radius of the inner solenoid S1 be R1 and the number of turns per unit length be N1. Let the radius of the outer solenoid S2 be R2 and the number of turns per unit length by N2. Let N1 and N2 be the total number of turns in coils S1 and S2. Thus, we have N1 is equal to N1L and N2 is equal to N2L. When a current I2 is passed through the coil S2, a magnetic flux is set up within the coil and this flux is linked with the coil S1. Let us denote this magnetic flux by phi1. Let this be the flux per turn of the coil. Then, the total flux linkage with solenoid S1 is N1 phi1 equal to M12 I2. Let this be equation 1. M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. The magnetic flux is equal to the product of the magnetic field strength into the area. The magnetic field strength B2 due to the current I2 in solenoid S2 is given by B2 equal to mu naught N2 I2. Let this be equation 2. Area of the coil in solenoid S2, A is equal to pi R1 square. Let this be equation 3. Multiplying equations 2 and 3, we get the value of the magnetic flux in the coil of solenoid S1 as phi1 equal to mu naught N2 I2 into pi R1 square. Let this be equation 4. Also, we know that N1 is equal to N1L. Let this be equation 5. On multiplying equations 4 and 5 and simplifying the right-hand side, we get the expression N1 phi1 equal to mu naught N1 N2 pi R1 square Li2. Let this be equation 6. Equating the right-hand side expressions of equation 6 and equation 1 and simplifying, we get M12 is equal to mu naught N1 N2 pi R1 square L. Let this be equation 7. Note that for these calculations, we neglected the edge effects and consider the magnetic field to be uniform throughout the length and width of the solenoid S2. Also, solenoids of equal length were chosen. This is a good approximation, keeping in mind that the solenoid is long, implying L is much greater than R2. Let us now consider the case in which current I1 is passed through the solenoid S1. This current produces magnetic flux, which is also linked with the solenoid S2. Let the magnetic flux per turn linked with solenoid S2 be phi2. Then, the total flux linkage with solenoid S2 is N2 phi2 is equal to M21 I1. Let this be equation 8. M21 is called the mutual inductance of solenoid S2 with respect to solenoid S1. It is also referred to as the coefficient of mutual induction. The magnetic flux is equal to the product of the magnetic field strength into the area. The magnetic field B1 due to the current I1 in solenoid S1 is given by B1 is equal to mu naught N1 I1. Let this be equation 9. Area of the coil in solenoid S1 A is equal to pi R1 square. Let this be equation 10. Here, we assume the flux due to current I1 through S1 is completely confined to the solenoid S1 only. This is because the solenoids are very long. On multiplying equations 9 and 10, we obtain the magnetic flux per turn through the coil of solenoid S2 as phi2 equal to mu naught N1 I1 into pi R1 square. Let this be equation 11. We also know that N2 is equal to N2L. Let this be equation 12. On multiplying equations 11 and 12 and simplifying the right-hand side, we get the equation N2 phi2 is equal to mu naught N1 N2 pi R1 square L I1. Let this be equation 13. Equating the right-hand side of equation 13 and equation 8 and simplifying, we get the expression M21 is equal to mu naught N1 N2 pi R1 square L. Let this be equation 40. Comparing equations 7 and 14, we get M12 is equal to M21. Let M12 is equal to M21 be equal to M, which is equal to mu naught N1 N2 pi R1 square L. Note that the mutual inductance is neither dependent on the current nor the magnetic flux. It is dependent on the geometrical dimensions of the solenoid. This expression is true when the medium within the solenoids is air. If the medium within the solenoids has relative permeability mu r, then M is equal to mu naught mu r N1 N2 pi R1 square L. This equality M12 is equal to M21 holds good for long coaxial solenoids and is far more general. Even though the inner solenoid S1 is much smaller than the outer solenoid S2, calculation of flux linkage with inner solenoid is possible as it is effectively immersed in the uniform magnetic field due to the current through the outer solenoid. Thus, calculation of mutual inductance M12 is easy. However, in this case, it is difficult to find the flux linkage with outer solenoid due to the current through the inner solenoid. This is because the magnetic field due to the inner solenoid would vary across the length as well as the cross-section of the outer solenoid. Thus, calculation of mutual inductance M21 becomes difficult. Let us now take a look at how a change of current affects mutual inductance. Let us consider an experimental setup in which there is a coil C1 that is connected to a galvanometer G and another coil C2 connected to a battery. EMF is induced in coil C1 wherever there is any change in current through coil C2. Let phi1 be the flux through coil C1 of N1 turns when current in coil C2 is I2. We know that N1 phi1 equal to Mi2. The rate of change of current is equal to the rate of change of flux. This means that dN1 phi1 by dt is equal to dMi2 by dt. The EMF induced in coil C1 is given by E1 is equal to minus d N1 phi1 by dt. This implies that E1 is equal to minus m di2 by dt. Remember, only flux and current change. Hence, m is a constant. This equation shows that a varying current in a coil can induce EMF in a neighboring coil. Let us now solve an example to reinforce our understanding of mutual inductance. A current I passes through the outer ring of two coplanar concentric loops of radii R1 and R2. R1 is much greater than R2. What is the mutual inductance between the two loops? The magnetic field induced by a current I at the center of the ring of radius R1 is B1 equal to mu naught I by 2R1. The flux through the ring of radius R2 is given by phi21 equal to B1A2. This implies that phi21 is equal to mu naught I by 2R1 into pi R2 square. Mutual inductance M is given by phi21 by I. On substituting the value of phi21 and simplifying, we get the value of mutual inductance as mu naught pi R2 square by 2R1.